So far, all we've been doing is trying to get used to a good way of talking about motion. We haven't tried to actually explain motion yet. In order to explain motion, we need to talk about forces. So that's what we'll start thinking about now. A force is basically just a push or a pull that can make something accelerate. And we've already hinted at that a lot whenever we talk about the acceleration due to gravity or the gravitational acceleration, the acceleration caused by gravity. We're hinting that there is this force, the force of gravity, that causes some kind of acceleration, the 9.8 meters per second pointing down acceleration. Anytime you're dealing with any situation that involves accelerations, you're probably going to have to think about forces at some time. And in any situation where you need to think about forces, it'll just about always be the case that the first thing you need to do is identify which kinds of forces are actually operating in that situation. So it's good to have a list of forces that you can keep in mind and be on the lookout for those forces and see if you can find them in any particular situation. In the Chapter 4 Blackboard file, I've got a list of all the forces that I'm going to mention here in just a few minutes. So make yourself a copy of that, and that's a handy reference to keep with you whenever you're dealing with any kind of force problem. So, first kind of force, one that we've already talked about, the gravitational acceleration from the Earth, also known as weight. And I'll just always use the variable W to refer to weight. And the weight is always a force that points down, or more precisely, it points toward the center of the Earth. It's a pull towards the center of the Earth. And at least for objects close to the surface of the Earth, it gets more complicated if you're out in space. But for objects close to the Earth, there's a nice simple rule for calculating the magnitude, the strength of the weight. It's just mass times g, mass times 9.8. You can see from this rule that mass and weight are closely related to each other, but they are not the same thing. Important to remember that. In everyday speech, we use words like mass and weight almost interchangeably, but in physics they mean something very, very different, and you'll get confused and you'll make mistakes if you don't remember that distinction. Weight is a force, gravitational force from the Earth pulling on everything. Mass is not a force, it's something else, and what it actually is something that we'll deal with shortly, after we're finished listing all the forces. So weight, that's one force. The next one is a so-called spring force or elastic force. Almost any solid object is elastic to some extent, but for a really elastic object like springs or rubber bands, things like that, we'll just call it a spring force. And what happens when the spring force is present? So just imagine this spring here. You're not stretching it, you're not squeezing it, it's just sitting there at its normal length. And then you pull on it, you stretch it, and being an elastic object, it's going to try to snap back to its original shorter length. That's what elastic means. If you stretch it or squeeze it or distort it in any way, because it is elastic, it tries to return to its original shape. So in this case, distorting it by stretching it, it's going to try to snap back to its original shorter length. But as long as you're holding onto the right end of the spring here, it can't snap back. It's trying to snap back, but it can't. And in trying to snap back, it's pulling on your hand. And that pull is the elastic force or spring force. And I'll usually refer to that with a capital F and an S subscript for spring. Same kind of thing happens if you squeeze the spring. Here's where the right end of the spring is at its normal length, but you squeeze it, so it is now shorter than normal, and the spring will try to snap back to its original longer length, but it can't because you're pushing on it. So the spring is trying to snap back this way, and in trying to snap back, it pushes on your hand. Then that push is another manifestation of the spring force. Right, as you can see from these two examples, the spring force always is trying to undo whatever kind of distortion has happened. If you stretch it to the right, it'll try to snap back to the left. If you squeeze it to the left, it'll try to push back, snap back to the right. So, spring force. There are two other kinds of forces that are very similar to this spring elastic force. They are, in some sense, elastic forces also, but we give them special names other than elastic force. Here's one. I'm holding these keys in my hand. They feel a weight force, a gravitational pull. They're pulled down by the weight force, the gravitational force from the Earth, but they're not falling. They're not accelerating because of that gravitational force. They're just staying put. That's because there's some other force just as strong as the weight force that's pushing the other way and canceling out the weight force. So that on net, there's really no force acting on these keys. There's a downward force, but there's an equal amount of force pointing in the opposite direction to cancel out the downward force of the weight. And that upward force that cancels out the weight is a support force from the surface of my hand. That's an example of a normal force. Normal is just a bit of jargon from geometry, which means perpendicular. Specifically, a normal force is a force from some kind of a surface, a push from a surface, and it pushes perpendicular to the surface. Normal is just a synonym for perpendicular. So the normal force is a push, and it pushes in a direction normal to the surface. Right? In this case, the surface that's doing the pushing is my hand, and my hand is a horizontal plane, so the push is normal to that, perpendicular to that, vertical. And another example, I'm leaning on the blackboard here, but I'm not falling over. And the reason I'm not falling over is because there's a push from the surface of the blackboard on me, pushing this way, and that push prevents me from falling over this way. And that push from the surface of the blackboard is a normal force. Right? A vertical surface, the blackboard, pushing horizontally on me. And then this, what I've written down here is just to say what normal force is. It's a push from a surface, and it's always perpendicular to the surface. Just the symbol for perpendicular there. Now, I said a few minutes ago that the normal force is a kind of elastic force, because what's happening in this case, the keys, for example, they feel a weight force, so they are pulled down, which means they're pushing into my hand. And because they're pushing into my hand, and the molecules at the top of my hand are squeezed a little bit closer together than they would be normally. And that set of molecules has some elasticity to it. If they're squeezed too close together, they will try to snap back to their original greater length. And as they try to snap back, they'll push up on the keys. And that's where the upward normal force from my hand comes from. Okay. And of course, in this case, my hand is pushing this way on the blackboard, so the molecules in the blackboard are squeezed together closer than they would be ordinarily, and because of their elasticity, they'll try to snap back to their original spacing, and in trying to do so, they'll push this way, which means they'll push this way on my hand. Okay, so that's a force that, when you look at it on a microscopic scale, is another kind of elastic force. Then there's one more force that behaves that way. If you look at it microscopically, it'll be another elastic force. Okay, the tension force. A tension is a pull, as opposed to a normal force being a push. A tension is a pull from a rope, or a chain, or a cord, or from, say, a muscle pulling on a bone, or a tendon pulling on a bone. And what happens in the a tension force, well, imagine you've got a rope and something is hanging from the bottom of the rope. That thing at the bottom, of course, feels a gravitational force, so it's pulled by that gravitational force, and since it's pulled, it in turn pulls on the bottom of the rope, and at a tiny microscopic level, it stretches the rope a tiny little bit. That is, the molecules in the rope are now stretched a little farther apart than they would normally be, and like any elastic thing, they'll try to snap back to their original closer spacing, and in trying to snap back, they will pull up on whatever it is that was hanging at the bottom, whatever it is that was pulling, stretching the rope. And that pull, caused by the elasticity of the rope, as the rope tries to snap back to its original shape, the molecules try to snap back to their original spacing, that pull is the tension force. Right. The normal force is a push, tension force is a pull. Okay, so those are four of the most common types of forces. You'll see them very often. Weight, practically everything that you ever deal with will have a weight force. Spring force, normal force, tension. So that's four forces. And then next on our list of forces are three different kinds of friction force. So the first, all right, the first kind of friction force is called kinetic friction, or sometimes sliding friction. It happens when there are two surfaces sliding across each other. You're pushing a big box across the floor. There'll be a sliding friction force between the floor and the bottom side of the box. And I'll use the symbol lowercase f for all of the friction forces, and then a subscript k for kinetic friction. So here's the box, and I'm sliding it to, say I'm sliding it this way. So the direction of motion is to the right, the velocity is to the right. Kinetic friction always acts to try to slow down an object, or at least keep it from accelerating less than it would have accelerated otherwise. In other words, it's going to point opposite to the velocity. The kinetic friction force will always make motion more difficult. And where the kinetic friction comes from is again like tension and normal force. It comes from something going on at the molecular level. There's the floor that the box is sliding across. Right? The molecules on the very bottom of the box will make weak but very real adhesive forces with the molecules on the top of the floor, and in order to move the crate at all, you have to break those bonds. You have to push a little harder and expend a little more energy to break those bonds, so it's a little more difficult to get the crate moving or to keep the crate moving. And that difficulty is because of this kinetic friction force, which exists because of those bonds that have to be broken, those bonds between the molecules on the bottom of the box and the top of the floor. So kinetic friction applies to any surface that is sliding across any other surface, and it's a force that will always be parallel to that surface, as opposed to the normal forces, which are also forces from a surface, but they're perpendicular to the surface. There's one kind of friction force when something is moving, another kind of friction force when something is not moving. And that's called static friction. Lowercase f for friction and subscript s for static. That's the algebraic symbol we'll use for static friction. And imagine this. Imagine a box that is very heavy, and as a result, when you push on it, you push, but it still doesn't move. It doesn't move. There's a force pushing to the right, but that doesn't cause the box to accelerate. That must be because there's some other force pushing the other way that is strong enough to counteract and cancel out your push. And that force that keeps something from sliding is static friction. Right. Kinetic friction happens when something is sliding. Static friction prevents the sliding from happening in the first place. It just, when there's static friction, the adhesive bonds between the bottom of the crate and the top of the floor are strong enough that your push can't break those bonds. The box stays stuck in place. And of course, as we know from trying to push heavy things, there's a limit to how strong this static friction force can be. You can push a little harder, and still the static friction force will be strong enough to match and cancel out your force. And push a little harder still, and still the static friction force can be strong enough to match and cancel out your push. But eventually, you're able to push hard enough that you can overcome that static friction and get the box moving. Eventually, you push with enough force that the static friction can't match, can no longer match, and can no longer be big enough to cancel out your push. So in other words, there's the static friction force can take on a whole range of values up to some maximum value. So if your push is less than the maximum possible static friction, then static friction will be able to match your push and cancel it out. But if your push is stronger than static friction could ever be, then static friction cannot match and cancel out your force, and you'll finally get some acceleration. You'll finally get the box moving. Third type of friction force is called rolling friction, and as the name suggests, if something is rolling, it's rolling because there is rolling friction. So just imagine a wheel moving that way. And there are two ways that it could move to the right. It could either move to the right while rolling, or this could just be a very, very icy road, and the wheel could slip or slide instead of rolling. Well, if it's really, really smooth and it just slides, it's sliding because there is not a sufficient rolling friction force to make it roll instead of slide. But if it's rolling instead of sliding, it's going to roll. If the wheel is moving left to right, it's going to roll that way. And it's rolling instead of sliding because right here at the contact point between road and wheel, the road is able to grab onto the wheel with enough of a strong enough molecular bond, strong enough adhesive bond between the molecules in the road and the molecules right here where the tire touches the road, can grab on to that. Road molecules can grab onto tire molecules well enough to actually push the tire molecules that way. This piece of the tire getting pushed means that piece of the tire is going to rotate a little bit, roll instead of just sliding. Like static friction, rolling friction as well prevents sliding, right? In the case of static friction, it prevents sliding and keeps the thing from moving at all. In the case of rolling friction, it prevents rolling and makes the thing, it prevents sliding and makes the thing roll instead. And in both cases, static friction and rolling friction, the direction of that friction force is opposite to the slide that it is preventing. In this case, I'm pushing this way, so if this box did slide across the floor, it would slide left to right. Therefore, the friction force, the static friction force that prevents that sliding must be pointing to the left. Similarly, if this wheel slid across the road, it would slide from left to right, so the rolling friction that is preventing sliding and making the wheel roll instead must counteract that slide, so the rolling friction must push to the left. The symbol that we use is, again, lowercase f for friction and then a subscript r for rolling. And then the rolling friction force points opposite to the slide that it prevents. The road molecules grab onto tire molecules right here and push them this way, which will make the tire rotate clockwise. One more force, just one more force that we need to talk about. And it's called drag force. We've already mentioned it a little bit. Anytime you move through any kind of a fluid, water or air, you'll collide with those water molecules or air molecules. And every collision is a tiny little backwards push. And the net result of all of those billions and billions of tiny little backward pushes could amount to a significant backwards push, and that's the drag force. Capital F and then a D subscript for drag. That's our usual algebraic symbol for drag force. And like kinetic friction, drag force always points opposite to the velocity. Something is moving this way, it'll collide with the air molecules or the water molecules, and all those collisions will be pushes this way on the moving thing. And the grand total of all those pushes is the drag force. One significant thing about drag force is that the faster you're going, the stronger the drag force gets. In a sense, that makes perfect sense, because if you're not moving, there is no drag force at all. If you're not moving, you're not colliding with any molecules that get in your way. So you have to move in order to collide with air molecules. You have to be moving in order to get a drag force. And if you're moving faster, well, you'll hit those molecules harder, and they'll hit back on you harder. And as a result, the drag force gets stronger. So we'll just put it this way, that if the change in speed is positive, that is something speeding up, then that implies that the drag force must get stronger, or the magnitude of the drag force gets bigger, the strength of the drag force gets bigger, or the absolute value of the drag force gets bigger. There's three ways of saying the same thing. The change in the strength of the drag force is a positive change. It gets bigger, stronger. And that'll we'll look at that in detail in a couple weeks, and that has some interesting consequences. But that's it for now. Those are all the forces that you have to be familiar with, and eventually you will get pretty familiar with them. And as I said earlier, the first step in thinking about any problem involving forces is to identify what kinds of forces are actually present at any particular time. And to do that takes a little practice. So that's the first thing we'll practice. Here's just an example of how to identify forces. Let's say Imagine somebody riding a bicycle downhill, and that person is going pretty fast, and in fact, say that person is speeding up. So here's the hill, and then there's the bicycle, and then the person on the bicycle, and just like we've been doing so far, where we just represent the moving thing, like in a motion diagram, where we represent the moving thing with just a dot, and don't aren't concerned about the individual parts of that moving thing. We'll just consider this this rider and the bicycle as just one little lump of mass moving downhill at a pretty high speed. And then, what are the forces acting on that thing? Well, obviously, the first one that should come to mind is weight. There is a gravitational force from the Earth pulling down on that person and bicycle. And remember, a weight force always pulls straight down, always pulls towards the center of the Earth, which is what we mean when we say straight down. So there's one force. And the bicycle and person are not falling and accelerating because of that force. So there must be some other force opposing that the straight down motion that you'd get from if weight were the only force. Well, here's one. Here's a surface in contact with the bicycle. And that surface is going to apply a normal force to the cyclist. The cyclist is pulled by the weight force, so the bicycle and person push on the road surface. That squeezes the road molecules a little closer together than they would normally want to be. They try to snap back to their larger spacing, and as they try to snap back, they push on the bicycle and the person, and that push from the surface of the road, any push from a surface, is a normal force, and normal means perpendicular, so it's pushing perpendicular to the road. Right? That's the direction of the normal force, because that's the direction that's perpendicular to the road. All right, there are two forces there. Any others? Yes, we presume that the tires of the bicycle are not sliding but are rolling normally. If the tires were sliding, of course, they'd be sliding this way downhill. Since they're not sliding and rolling instead, it's because there's a rolling friction force that prevents sliding. And that rolling friction force always points opposite to the direction of the slide. So there's a rolling force pointing that way, uphill. And finally, I said the cyclist is moving at a high speed. Well, we know that at high speeds, drag force is stronger than it is at low speeds. So it's quite likely that there's a significant drag force from the air on the cyclist and bicycle. And of course, drag force always points opposite to the direction of motion, opposite to the velocity. So drag force velocity is that way. So drag force must point the opposite way, uphill. Every other situation you would analyze the same way. Just take your list of forces and see which ones are present. One important clue when you're looking for trying to find the forces is to look at everything that is in contact with the object that you're interested in. In this case, what was in contact with the the person and bicycle, it was just the road and the air. But it's almost certain that the things that are in contact with the moving object will be the sources of some forces on that moving object. Right? In this case, the road in contact with the moving object was the source of a normal force and a rolling friction force, and then the air in contact with the moving object was the source of a drag force. Every force except weight is like that. Every force except weight is a contact force. Every force except weight comes from something that's in contact with the moving object. So look at all the things that are in contact with the moving object, and other than weight, that's where all the forces will come from. Okay, and then in the lecture exercise and then in class, you'll have a lot of practice here, just identifying force in all kinds of different situations.